Thank you so much. This is a kind of postponed from maybe last year. I think I've been trying to come here for about 18 months or so, really. So darn that pandemic. But I finally made it in here from the hills of Marple in one piece, just about, despite the best efforts of the trains. So yeah, tonight I'm going to talk about how we look inside volcanoes. And this is work I've been doing in conjunction with Craig McGee and Chi Liang Sun, so the two people named on that slide. I'd also like to start off as well by acknowledging the contribution of people who provide us with data and software and hardware. Without them, academics like me wouldn't be able to do half of the nerdy stuff we want to do. So I'm aware we have a broad church of people in this room. So I'm going to start off very gently and sort of introduce you to some of the key terms I'm going to use during this presentation, because I don't want anybody to be left behind. I was always told by my PhD supervisor that in a talk you should aim for people to leave the room feeling super clever. Okay, that's my job in the next 40 minutes, is for you to go home and regale your friends with tales of how to look inside volcanoes. So let's get started and think about, what magmatism is. And most of you will be familiar with the term magma or lava. And we often get magma generated, as you see here, deep within the Earth's crust, and it rises up through these layers of rock above. So these layers of rock are often sedimentary rocks, these kind of colors in here, these stripes. And you can see a number of different features which are forming there. We have these sub-vertical sheets of magma, which we call dikes. We have these sub-horizontal sheets of magma, which when they crystallize become igneous rock, and they're called sills. And we have these features here, which are called volcanoes, obviously. And you can see that those volcanoes are underlain by this very complicated feeder system. So the magma is not just shooting up a tube to be fed into the volcano. It's actually being intruded into the rocks below in a very complex way. We also have these features in here which have a flat bottom and a rounded top, and they're called laccoliths. Fancy word you can tell your friends about you learned tonight. Laccoliths, okay? And above that laccolith, can you see the Earth's surface is domed up? The Earth's surface has been uplifted, and that's because you're forcing magma into the Earth. The magma's inflating, and the Earth's surface has to deform to accommodate that magma. So you get a fold above. And I'm going to talk about those in some detail tonight as well. So let's keep the video going. You can see that eventually that magma cools and it solidifies, okay? And you can see it solidifies now, so it's gone from orange to this dark grey. So that's magma becoming igneous rock, yep? And if we keep going, you see the laccolith, you see the volcano. Now, one of the challenges is, if I just skip back and run that video again, one of the challenges is, oftentimes, this is what we see. So we have this magmatism happening millions and billions of years ago. But what we're left with as geologists is this. We walk out into the field, we call it. We walk out into the areas in the hills. And we're left with this, right? We're left with a volcanic stump, if you will. And then we have to try and guess what all is going on underneath in here, because all we're left with are these, what we call pseudo 3D. So they're not fully 3D, but pseudo 3D snapshots of all the things that were originally in place a long time ago. Why does it matter? Well, it matters how magma moves through the Earth's crust and how volcanoes are constructed by that magma because of this. We have this co-location of people, infrastructure, and volcanoes. And volcanoes can be dangerous. This is El Popo, this volcano which sits just behind Mexico City, a city with a population of just under 9 million now. Mexico City has the unfortunate situation of being not just next to El Popo, a very active volcano, but it's also built on lake bed sediments, so very weakly lithified sediments. And I don't know if you remember, a few years ago, Mexico City actually received a magnitude 7 plus earthquake, which damaged a lot of buildings. Obviously, the people who were the founders of Mexico City didn't know that the volcano was going to erupt and know that there were going to be earthquakes in the eastern part of the Andes at the time. But that's what we're dealing with now. We have populations encroaching into areas which are subject to these geohazards like volcanoes. So there's a humanitarian reason to understand how magma is transported through the Earth and how volcanoes are built. How do we answer some of those questions? How do we typically understand how volcanoes work? Well, this is the classic shot, isn't it, of the hero geologist in a heat-resistant suit, sticking the hammer. This is one we show at open days. Sticking the hammer into lava to get what we call a zero-age sample. So what they're doing is collecting a sample of lava, which is the name for magma when it comes out at the Earth's surface. Another nerdy tip for you. Magma and lava are the same thing. We just call them different things depending on where they are. But this is lava. Sticking the hammer in, they're going to cool that down in a bucket of water. They're going to cut it into thin slices and look at them down a microscope and look at the composition of the mineral types and the chemistry. And from that, they'll try and work out where that magma was generated in the Earth's crust. And critically, oftentimes, what people are looking for is how viscous or sticky that lava is. Because the stickiness of lava controls how fast it moves, and how fast it moves is a really important hazard if you think about living next to a volcano that's erupting lava. So that's the kind of classic thing, you know, all dangerous, all heroic. We make TV shows about this sort of stuff. We might even make TV shows about this sort of stuff. This is somebody here sampling volcanic gases, carbon dioxide and sulfur dioxide. And that's because often around volcanoes we have volcanic fumaroles. And what they're doing is collecting that gas and they're reading what the gas measurements are. That's because, you know, these gases are normally just coming out of volcanoes, but sometimes when volcanoes are about to erupt, these gases increase within those particular fumarole vents. And that's because there's new magma coming into the volcanic system. It's recharging the magma. It's actually inputting more gases of those types and others, and then measuring it. So if you can establish a baseline of gas, and then you can see a spike in gas, and then the volcano erupts, you could use it in a predictive sense. Okay, but you need that baseline to try and understand what the volcano normally looks like. We can also do things which are not geological, which are not geochemical, but we can do things geophysically. We can actually look directly inside the Earth. What we're looking at here is an image through Mount St. Helens. Many of you will be familiar with the eruption of Mount St. Helens in 1980. I'll lose my geology badge if I get that wrong. I think it's 1980. And this is the Earth's surface. And what you're looking at here, the blue colors are where sound waves essentially are traveling relatively quickly through the Earth. The red areas are where sound waves are traveling quite slowly through the Earth. Now, the reason there's a difference there is because the red areas here are what we call magma. They're mushes. And the sound waves don't travel so quickly through something which is gooey, essentially. Whereas the blue areas where the sound waves are traveling very fast is where we have crystalline rock. That's where we have magma that has become crystalline. So what you're actually looking at here, which I still find amazing, bearing in mind that's 5 kilometers for scale there, 5 kilometers for scale there, you're looking at the magma chamber under Mount St. Helens. So that's what the magma looks like underneath that giant volcano, which is active, it's been active quite recently as well. We're not just limited to looking at these geophysical images, looking at sound wave derived images. We can also lay on top of that these pink dots, and these pink dots are earthquakes. So what's been laid on here is people have located where earthquakes are in the Earth's subsurface. It's been laid on top of this image, and you can see that those earthquakes are defining a really well kind of structured conduit, aren't they? They're vertically occurring underneath the volcano. That's happening because as magma forces its way through rock, the rock breaks, and that release of energy is the earthquake. So you can see that there's a very active magma conduit underneath Mount St. Helens, but there's areas of magma being stored elsewhere, which is aseismic, we call it. There's no earthquakes in the gooey stuff. Why? Because the gooey stuff can't snap, right? The rocks can break, they're brittle. The magma or mush can't. So from that, we can get a sense as to what's going on inside that volcano. The other thing we can do is we can actually instrument volcanoes. And this I'm showing here is this was actually a tilt meter, and it was before I was born, and I'm quite old. This is a tilt meter, and what it is you can see inside there's a plate sitting inside. So you stick this canister on a volcano, and if the volcano tilts, that plate stays still. So then you've got an angle, and if it's flat, you don't. So if it tilts, that plate stays still. So you're measuring the angle between the plate and the rest of the body of the thing. So if you put that on a volcano, you can actually see how the Earth's surface deforms. So if you look at time on the x-axis and the amount of tilt on the y-axis, I'm a simple guy, I like simple scales. You can see in here that as a volcano starts to inflate, as magma comes in, it tilts. The eruption begins, we have large amounts of deformation, and then as the volcano stops erupting, you can see the tilt decreases. We can use tilt meters, but we can also use things which are known as, we can use something called INSAR. So INSAR is satellite-derived images of the Earth's surface. They can get resolution down to about 1 millimeter, And so we have these continuous records of the Earth's shape from satellites which are orbiting. And these are really powerful ways of actually understanding how volcanoes. So some of you remember the volcanic eruption in Iceland early this year? You remember it eventually erupted, I think, in February? Do you remember there was this whole like 2 or 3 months of earthquakes racing back and forth along the Reykjanes Peninsula, just south of Reykjavik? So they knew there was magma coming into the system. They could see the Earth was going up by 2 centimeters from satellites, and they could actually predict or pinpoint exactly where the volcano eventually erupted. So it's incredible technology.